Well, hello there. Mr. Sutton bringing you the AB Calculus 614 Extra Practice number 6 solutions on volumes with known cross-sections. On this problem, we're given R, the region in the first quadrant, bounded by 2 secant of x, the line pi x equals pi over 4 in the x and y axis. So this region R is the base of a solid whose cross-sections perpendicular to the x-axis are semicircles. What's the volume of the solid? Okay, so let's see here. We need to basically integrate semicircle slices from left to right to get this volume. So left to right means 0 because we're going from the y-axis to pi over 4. Those are going to be our limits of integration. And we need an area formula. For semicircles, in general, I can write a of x equals 1/2 pi r squared. But in order to actually integrate this, which I need to do without a calculator, I need to express this in terms of x. So what's the radius now in terms of these functions here? Now these semicircles, they're going basically in an up-down fashion from the bottom to the top of this bounded region. The bottom of the bounded region is just the x-axis. The top is this 2 secant of x function. So the distance then from one end to the other is just 2 secant of x. So that's the diameter of these semicircles. But we want half of that to get the radius. So we're going to do 1/2 pi times 1/2 of 2 secant of x. And square all that. So half of 2 secant of x. This right here is our radius. So I'm going to have to integrate this whole thing from 0 to pi over 4. To do that, let me clean it up a little bit. So out in front, I can write this as just pi over 2. And in here, well, this is just secant of x squared. So I'm just going to write secant squared of x there. So now I'm doing the integral from 0 to pi over 4. I'll bring this pi over 2 out in front just to make my life a little bit easier. And inside, I've got secant squared of x dx. Antiderivative of secant squared, well, this works out nicely. That's just going to be tan of x. So I've got 1/2, or pi over 2 rather, times tan of x evaluated from 0 to pi over 4. So this is pi over 2 times tan of pi over 4 minus tan of 0. Tan of pi over 4 is just going to be 1. That's one of those special ones you should memorize, tan of 45 degrees. So we've got 1 minus tan of 0 is just 0. So when all is said and done, this just comes out to pi over 2, which gives us choice A. On this problem, we've got this R region between the graphs of 1 minus x cubed and 1 minus x, and this is the base of a solid. For the solid, each cross-section perpendicular to the x-axis is a square. So we basically have these squares rising three-dimensionally out of this base area. We want the volume of the solid that these squares make up. So let's first get the limits of integration on this one, because we're going to have to integrate basically from left to right. So these two functions are going to equal each other at, well, it looks like 0. Let's see if that's actually true. If I plug in 0, I have 1 minus 0 cubed and 1 minus 0. That comes out the same on both sides. It also looks like they cross over here at 1. Well, 1 minus 1 cubed is 0. 1 minus 1 is 0, so that is also true. So it's 0 and 1 for sure. And now we have to figure out what we're actually integrating. Since we have cross-sections that are squares, we're essentially chopping the solid up into square slices and adding them all up with our integral. So the formula for a square, in general, I'm going to say a equals s squared, but I need to express this in terms of x in order to actually integrate it. So the side of each square, these squares are perpendicular to the x-axis, so they're going this way. These are up-down sides of the square. So that means that the square side is just going to be the distance between these two functions, which is to say 1 minus x cubed minus 1 minus x. And we're going to have to square all of that stuff. So this is what I have to integrate from the interval from 0 to 1. I'm going to clean this up a little bit before I go to the integral here. So let's see here. I can have a minus 1. That's going to cancel out with the 1 over here. I've got a plus x squared. So when the dust settles, this is negative x cubed plus x squared. All of that inside these squared parentheses. Now let me integrate that from 0 to 1. So we have volume equals integral from 0 to 1 of this stuff. but I'm going to expand this first. If I'm doing this by hand, I have to use the fundamental theorem, take antiderivatives, all that stuff. So let me expand this out. Using a squared plus 2ab plus b squared, we have this first thing squared, which is going to be x to the sixths. And then we have to multiply these together and double it for the middle term. So that's going to be, let's see here, negative x to the fourth if we multiply them, so negative 2x to the fourth then. And then finally squaring this last term, we've got x squared, all of that with a dx after. Now I'm going to use the reverse power rule to take my antiderivative. So here we bump up to a 7 for the exponent. Dividing by that, we have 1 over 7, x to the 7th. Next, this exponent becomes a 5. Dividing by that, we have negative 2/5 x to the 5th. And finally, this becomes a 1/3 x to the 3rd, all evaluated from 0 to 1. We have to do this by hand, and we have to simplify it, so this is going to take a little bit of doing here. We have all this stuff with 1 plugged in, minus all this stuff with 0 plugged in. And really the only bright side out of this is that you're plugging in 1 and 0. 0 is going to zero out that entire second bracket, so we don't really have to worry about that. That's really good. Over here, though, we have 1's getting plugged into all of these. So we essentially get all the fractions that these are next to. We have 1 over 7 minus 2/5 plus 1/3. So really nothing changes except for the coefficients are still there without everything else. And I do have to simplify this to get one of these answers. No calculator allowed. All right, well, this boils down to, do you know how to work with fractions? So to get our common denominator, we need something that 7, 5, and 3 all go into. So let me see here. 7, 5, and 3 don't go into that. 7 times 5 is 35, but 3 doesn't go into that either. If we multiply that by 3, that's going to be 105. So we need a denominator of 105. All right, well, I'm going to have to multiply this first fraction by 15 over 15. So that's going to be 15 over 105. This next fraction I have to multiply by 21 over 21. So this is going to be minus 42 over 105. And finally, this last one, this is going to be 35 over 105, multiplying by 35 over itself. Let's keep going. We've got 15 minus 42. That's going to be negative 27. And then negative 27 plus 35, that's going to be 8 over 105. So that ends up giving us answer choice A. For this calculator-based question, we have the base of a solid in the first quadrant being bounded by the x-axis and y-axis and this crazy-looking graph here. Let me graph this out and see what we're looking at. So I've entered this function in my y1 and the y equals. Let me go with a zoom 6. Not really sure what my window is going to be on this. All right, so let me go zoom in a little bit more there. Maybe zoom 4. Get a closer look at what's happening near the origin. So this is our bounded region between the y-axis, the x-axis, and that function they just gave us. So now we have a solid that's essentially growing out of that. For this solid, each cross-section is perpendicular to the x-axis is a rectangle whose height is 3 times its width in the xy plane, and we want the volume of that solid. So in order to do this, I'm going to have to integrate an area slice across that whole interval. Now, what is our interval going to be? What are our limits of integration? To see that, well, we know that we're bounded, if we look back here, we're bounded on the left at x equals 0. So we're just wondering on the far right, what's the right boundary of this shaded area or this bounded area? And it's kind of hard to tell just by looking at the graph. We could certainly find the intersection using the grapher. But honestly, if you just set this thing equal to 0 and solve, you're going to see that if you zero out the numerator with x equals 2, that's going to get the whole thing to equal 0. So we have 2 as our right limit of integration, our upper limit of integration. Now we need to figure out what the integrand is. What are we actually integrating? So I'm chopping this up into rectangle slices. And each of these rectangles is essentially, it's perpendicular to the x-axis, and it's growing 3-dimensionally out of this base area. Now they told us that the height is 3 times the width. The width, basically the base of the rectangle. So that's going to kind of be our way that we relate everything back to x's. In general, now I'm going to write that the area of my rectangle, the a of x here, which I'm going to need to integrate, is base times height. But again, the height is 3 times the base. So we can write this as b times 3b, or 3b squared. And now I still need to write this in terms of x to integrate it. So if you just look at the graph again, the base of these rectangles, the width of the rectangle, is just this distance, this vertical distance here, from the x-axis to the function. So b is really just this f of x function right here. So my area of x is really just 3 times f of x squared. So now to get the volume, I just have to take the integral from 0 to 2 of this a of x function I just wrote, dx. Let me do that on the calculator. So for this one, I'm going to go with Math 9 to get my integral. I have 0 to 2 as my limits of integration. And in here, this a of x function, this is just 3 times f of x squared. I stored f of x as y1, so I can just do 3 alpha trace y1 and then square that. And I'll put an x next to my d there. Press enter. Hope for the best. We got about 3.012. So that's going to be answer choice D. On this no calculator question, the base of a solid is a triangular region in the first quadrant bounded by this line and the x and the y-axis. So for the solid, each cross-section perpendicular to the x-axis is a square. What's the volume of the solid? So we have this triangular region, and we have these squares kind of growing out of it three-dimensionally. Now, let's get the limits of integration, because we're going to have to do some integration here. We're going to have to integrate some square areas over an interval. So I know that since we're bounded by the y-axis, my left limit of integration is going to be 0. But now on the right side, I need to know where this line here is crossing the x-axis, and that'll tell me how far to the right I need to go with my integral. So if I set 4 minus 2x equal to 0, I can quickly see, if I subtract 4 and divide by negative 2, that x is going to be 2. That's going to be my upper limit of integration in my integral. Let me get my function that I'm plugging into the integral. So in general, since my cross sections are squares, let me write a of x equals s squared, just as kind of a starting point. But now we have to replace this s with something that actually has x's so that I can integrate this thing. Well, the sides of each of these squares is basically going to be the distance between the lower part of the bounded region to the upper part. So from the x-axis to this line, 4 minus 2x. Well, that distance is just represented by the function 4 minus 2x. So the side of each of these squares is just going to be 4 minus 2x. So if I square that, I get the area of my square cross-sections. So now I have to integrate this from 0 to 2. So I'm going to go integral from 0 to 2. This is going to be my volume now of this stuff, dx. But now since I have to do this by hand, I'm actually going to have to expand this out and take antiderivatives. So let me just expand this out with a squared plus 2ab plus b squared. So 4 squared is going to give me 16. And then if I multiply these together, that's negative 8x, and I have to double that for the middle term. So negative 16x. And then squaring this last piece, this is going to be plus 4x squared, all with a dx after it. Using my reverse power rule from left to right, I've got 16x for that antiderivative. And then this is going to be an x squared. Dividing by 2, we have minus 8x squared. And then over here, this bumps up to a 3. Dividing by that, we have plus 4/3 x cubed, all evaluated from 0 to 2. So I've got all of this stuff with 2 plugged in, minus all this stuff with 0 plugged in. Now, if this were a free response problem, I could just stop here. Unfortunately, I do need to simplify so I can match one of these answer choices. So the good news is all this stuff with zeros is going to cancel out and just be gone. So we just really have to focus on this left bracket here. Going from left to right, we have 16 times 2, that's 32. This is 8 times 4, which is also 32, and I'm subtracting that. So these first two terms actually cancel out. So really the answer is just going to be this last term. We have 2 cubed is 8 times 4 is 32. So that's 32/3. And when these 32's cancel out, all that's left is that 32 over 3, giving me answer choice C. For this problem, the base of a solid is the region in the first quadrant bounded by sine of x and the x-axis on the interval from 0 to pi. And for the solid, each cross-section perpendicular to the x-axis is an equilateral triangle. Well, that ought to make it easy, right, if all the sides are the same. We want to know the volume of the solid. So let me graph this situation out just so we can get a visual here. It is a graphing calculator problem, so why not? So I've got sine of x entered as my y1, and my interval is 0 to pi. So let me go to Window, and let me set that from 0 to pi, x min to x max, and zoom fit this thing. So here's the sine function between 0 and pi. Now they're telling me I've got these triangular equilateral triangles that are basically perpendicular to the x-axis. So you can think of like a triangle standing up, and the lower side of the triangle is this line running from the x-axis to my sine curve here. And these things are essentially popping out of here in a three-dimensional fashion, and we need to figure out the volume that happens when we add up all those triangle slices. So if I'm taking a bunch of triangle slices and adding them up, I'm taking an integral. My limits of integration are just going to be 0 to pi, but now I need to know what area formula I'm actually using. So let me draw a triangle here. And since this is an equilateral triangle, we know that all the sides are the same. Now the crucial part of this is that the base of this triangle is going to be the distance from the x-axis to the sine curve. It's essentially going to be sine of x. So if we can write the area of this triangle in terms of the base, we can then plug in sine of x for that base and have a formula with an x that we can integrate. So all these are going to be the same. This side's the base, and these two sides then are going to be equal to the base. And that's great as far as it goes. The tricky part here is that the area of a triangle is base times height, and we don't have the height right off the bat here. To find it, there's a few ways you could do this. Probably the most straightforward, in line with what you've already learned, is just dropping an altitude here and figuring out this side using special triangles. Now, since this is an equilateral triangle, that means that the angle that you just cut in half there, which was initially 60 degrees, that means you cut it into two 30-degree pieces. So we've got 30 degrees here, 60 degrees still over here, and this is a 90-degree angle. So that is a 30, 60, 90 right triangle, and we know a few things about the ratio of the sides there. The 30 side is whatever it is, I'll call it S. The 60 side is going to be the 30 side times radical 3, and we know that the 90-degree side, the hypotenuse here across from the right angle, is always twice that short 30-degree side. So in terms of B, because I want to relate this height here to B, we don't know the height right off the bat, but we do know that this side here, this little side of this triangle, this right triangle on the right side here, is going to be half of B, B over 2, because I just chopped this whole side in half, so this little piece must be B over 2. That's the 30-degree side. That's S essentially. Now to get the 60-degree side, I need to take that B over 2, that S, and multiply it by the square root of 3. So this height here I could express as B radical 3 over 2. And now putting everything together, in general, my triangle height, A of x, is going to be 1/2 base times height. But in this case, the height is just going to be the base times radical 3 over 2. And let me just write b's there. There we go. Now, if I clean this up a little bit, I can multiply these to get a b squared. And also, I'm going to have a radical 3 and all of that over 4. So this is kind of a simplified version of everything I've done there. This is the area of my triangles expressed in terms of just the base. Now, the base, remember, is just going to be equivalent to sine of x. It was just the distance between the x-axis and sine of x, which is just sine of x. So I really have sine squared of x radical 3 over 4. This is what I now need to integrate over my interval. So remember that interval was from 0 to pi, so I have volume equals integral from 0 to pi of, well, I'm just going to write a of x dx in here, but I am going to have to do all of this on the calculator. So I'm going to do some work in my y equals now. I'm actually going to enter this a of x function as y2, and then I don't have to worry about fitting this inside an integral. I can just take the integral of y2 from 0 to pi. So I'm going to need a fancy fraction for this. So let's see, alpha y equals n over d. At the top, I've got sine squared, but sine is just this y1 function up here, so I'm just going to do alpha trace y1, and I'm just going to square that. And I mean, this is a good move if you don't really know where you're supposed to stick the second power when you're doing a sine function. It turns out you just put it out here outside the parentheses that has the x in it. But if you didn't know that, you could just do y1 squared. And now we have to multiply that by the square root of 3. And all of that's going to be over 4. So this whole thing now is my a of x function. Let me quit out of there. And I'm now going to do math 9 for my integral. We're going from 0 to pi. And I'm just going to do alpha trace y2 because that's where I just stored my a of x function. Put a dx there, press enter, and that all comes out to 0.680, which gives me answer choice A. For this problem, the base of a solid is the region in the first quadrant bounded by the x and y axis and the graph of 3 minus x over x plus 1. For the solid here, each cross-section perpendicular to the x-axis is a rectangle with a height twice the width. We want the volume of the solid. Well, let me start by just graphing this function to see what my base region looks like. So there's my function in my y equals. Let me do zoom 4 on this. So there's my area that these rectangles are popping out of, essentially, bounded by the y-axis, the x-axis, and this function we just graphed. So now, in order to figure out the volume of this thing, we're going to need an integral, which means we need to know the limits of integration, basically the left and right boundaries of that area that we just drew out. So we know that we're starting at 0 on the left side because the y-axis is one of our bounding curves. But for the right side, we need to know where this graph is intersecting the x-axis. Now that looks like it might be 3, but I mean, you can actually just figure this out by setting this curve equal to 0 and solving. We see that to zero this thing out, we need to make the numerator 0, which means, yes, we do need the x value, 3, to do that. So my integral is going to be from 0 to 3. All right, so what am I actually integrating? What is the integrand? What's the function? Well, we have rectangles. The area of those rectangles, in general, I'm going to write a of x, is going to be base times height. But they told us a little bit more about these rectangles. They said that the height was twice the width, which is to say twice the base. So I can write b times 2b, or 2b squared. And now what is the base of the rectangles? We can't just write base here because we need something in terms of x in order to integrate this area function. So going back to my graph, the base of the rectangles is just the kind of, each of those is a vertical strip that is running from the x-axis up to this curve here. So the base of the rectangles, the value of that each time at each x value is just going to be this 3 minus x over x plus 1 function. So I'm going to write in here then, and since this is f of x, I actually called this f of x so I wouldn't have to rewrite it. This is just going to be 2 times f of x squared. So let me integrate that now from 0 to 3, 0 to 3 of a of x dx. It's time for the calculator again. So to make this happen, I'm going to do math 9 for my integral. We're going from 0 to 3. And my a of x function, I'm just doing 2 times f of x squared. So 2 times, and I actually don't have to rewrite all this because remember, I stored this as y1. So I'm just going to do alpha trace y1 and square that. So that'll save me some time. Put an x next to the d, press enter, and we've got 7.819 for that volume. So that's going to be choice D. For this calculator-based free response problem, we have an f function defined by this crazy-looking monstrosity here between 0 and 3, and then we have a g function that's continuous and decreasing on 0 to 3, and they're telling us g of 3 equals 0, but they're not really telling us a whole lot more about the g function. So we've got two graphs here with f and g involved. We see here on the left side, we have the f region and the g region. Well, f is actually both of these regions, r and s, and g just has this r region under it. And region r, they're giving us the area of that. It's about 3.24125, okay. And region s, Well, they didn't actually tell us what region S is. We're actually going to find that in part A. They did show us a little bit more about this other graph, though. This is region T under the function g of x squared, which is kind of random, and they gave us that area. All right, so our first task, based off of all this information, it's kind of information overload, we're supposed to find the area of region S. So just in general, if you're trying to find area, you're essentially doing an integral from left value to right value of top minus bottom function. So we essentially need to take the integral from 0 to 3 of, well, f of x. So I have integral 0 to 3 f of x. Now, you got to be careful, though, because that doesn't give us just the S region, which is what they asked for. That integral is going to give us S plus R. We want to chop out that R area. We don't want to include that. So we have to subtract the R area that they gave us, this 3.24125, subtract that, and if we do that on the calculator, we should end up with our answer. Let's do it now. Now, I've got a feeling I'm going to need to use this f of x function more than once, so I'm going to put it in as y1. I mean, honestly, even if I was only using it once, I would probably do this, so I don't have to write it on top of doing other things. So let me quit out of there now that I've entered it in y1, and I'm doing my integral, so math 9, from 0 to 3, and I'm just taking the integral of f of x, so that's just alpha trace y1 dx. But now I have to subtract this 3 point whatever stuff. So let me subtract that, 3.24125, and all of that equals 4.920 if I take it out to 2 decimals. Or actually, I should say 3 decimals, but you don't have to write that 0 there. For this part of the problem, they want us to find the volume of the solid generated when S is revolved around the horizontal line y equals -3. So we have a horizontal line somewhere in here below the x-axis. That's not drawn to scale, but it is where it is. It's somewhere down there. So to find this volume, well, first off, our limits of integration are going to be the same as before. We're going from 0 to 3 because those are the left and right boundaries of the region S. But now we have to think of the area. If you're doing a solid of revolution, which we are here, our cross-section, our area cross-section that we're taking slices of and adding up, those are either going to be disks or washers. Now, since I have a gap between the region I'm revolving and the axis of revolution, that means I have to use washers. So I'm going to go with a of x equals pi times big R squared minus little r squared. And now for big R squared, that's going to be the distance from the axis of revolution to the outer function here. So that's going to be basically f of x minus -3, or f of x plus 3. And for little r, that's going to be the distance from the closer in function to the axis of revolution. So that's going to be g of x minus -3, or plus 3. So putting this all together then in a form that I can actually use my calculator on, I can say my volume notice I said a sub 1 here, because I'm going to use another area formula in the next problem, but I can say my volume is going to be pi, which I can take outside the integral, times the integral from 0 to 3 of, and now I'm basically just doing big R squared minus little r squared inside here. So that's going to be f of x plus 3, the whole thing squared, minus g of x plus 3, whole thing squared, dx. But I'm not quite where I can use my calculator. I can use my calculator with the f function because I already know what f of x is. I cannot do that with the g function, though, because they didn't actually tell me what g was, other than g of 3 is 0. I mean, maybe that'll be helpful. I don't know. But we can't use even that just yet. So in order to do this, I'm actually going to split this integral up. So let me see here. I can just keep this f of x plus 3 squared stuff where it is. I'm going to give that its own integral, and I'm going to have pi times a big parentheses with all this stuff in it. So first item in the parentheses, integral from 0 to 3 of f of x plus 3 quantities squared. So this just gets its own integral. Now, my other integrals, I'm going to have actually 3 integrals, basically I'm going to expand this g of x plus 3 term, and then I'm going to split it up into 3 different integrals. And each of them I'm going to be subtracting because I'm subtracting this whole thing. So my first integral is just going to be, if I square this first thing, I'm just going to get g of x squared inside the integral from 0 to 3, and I'm subtracting that. The next term, if I were to expand this, my middle term, the whole thing I'm using is basically a squared plus 2ab plus b squared. So for that middle term, I have to multiply these together and double it to get that 2ab term that I always get when I square a binomial. So that would end up being, let's see, g of x times 3 is 3g of x. We have to double that, though, so that would be 6g of x. So I have to subtract the integral from 0 to 3 of 6g of x then. And the 6 can be inside or outside, doesn't really matter. I'm going to keep it outside, though, and you'll see why I do that in a sec. And then finally, we have a 3 being squared, which is just 9. So I'm subtracting the integral from 0 to 3 of 9 dx. And now I have to figure out what all of this equals using my calculator. Well, the calculator, again, will help me out with this f of x stuff. But what am I going to do for this g of x squared? Well, this is talking about the area under the g of x squared function between 0 and 3. And it just so happens they gave us a graph of g of x squared with an area under it, and they told us the value of that area. They said this region T here had an area of 5.32021. So this integral from 0 to 3 of g of x squared is just this area of T right here. Okay, so that helps a little bit, but what about this g of x stuff here? Well, for g of x, that is this function right here. They gave us this function. This is essentially saying 6 times the area from 0 to 3 under g of x. We actually know the area under g of x from 0 to 3. In this graph right here, that's the area R. And R, they told us, has an area of 3.24125. So g of x itself equals that number, so I can plug that number in and multiply that by 6. And then for this last piece, well, this isn't going to be so bad. I could do this without a calculator, actually. This is just the area of a rectangle with a base of 3 and a height of 9. So 3 times 9 there is just going to give us 27. All right, let me plug all that in my calculator now. So getting the setup was challenging. Plugging this in the calculator may be even more challenging. Let me start by doing pi and open a parentheses. And now we need the integral from 0 to 3 of f of x plus 3 squared dx. So let's go back there, and let me do math 9. To get my integral, we're going 0 to 3. And again, we had f of x plus 3, the whole thing squared. So let me open another parentheses in here. For f of x, I actually stored that as y1. So alpha trace y1. And then we're adding 3 to that. Close the parentheses, square it. Put a dx on this thing. And then we keep going. So now we're subtracting this g of x squared stuff. And we said that that had a value of 5.32021. So let me plug that in. Minus 5.32021. Got to enter this carefully. Next, we're subtracting 6 times the integral from 0 to 3 of g of x. So we're going to be doing minus 6 times. And we said g of x, that was 3.24125. So let me put that in there. 3.24125. Great. Close that. And then finally, we said that this last integral just had a value of 27. So let me just do minus 27. Close my parentheses. And, oh boy, let's hope for the best on this. Press enter. Supposedly 156.264. There it is. For this last piece of the free response, they're telling us region S is the base of a solid. So this right here is the base of some solid. For this solid, each cross-section perpendicular to the x-axis is a rectangle with a height 7 times the length of the base in region S. Write but don't evaluate an integral expression for the volume of this solid. Well, we need limits of integration. Those are just going to be 0 to 3, the same as the S area limits of integration. we also need a formula to plug into the integral. So my formula in general, it's going to be a rectangle formula. I can say, I'm going to write this as a sub 2 of x equals base times height. And I'm saying a 2 down here so I don't confuse it with the area formula that I created for part B. So now base times height, we actually know that the height is 7 times the length of the base. So I can rewrite this as base times 7 base. So 7b squared then if I simplify that. And what is the base in terms of x? Because we need this in order to actually integrate it. Well, the base is just a vertical strip going from the bottom to the top of this S region here, all the way across. So that's going to just be the f function minus the g function. So I'm going to have 7 times f of x minus g of x, whole thing squared. That's my area that I now have to integrate. So the volume then is just going to be the integral from 0 to 3 of, and now there's options here. You could write a sub 2 of x dx since you just defined that, or you could write out this whole thing and stick a dx after it. Either of those would be acceptable. And they said do not evaluate, so we will definitely take them up on that and not evaluate. Done.